Hello everyone, we are from Group 19 and we will present about the extended Debye-Huckle Law. We are the presenters of today's topic. I'm Thanussha Parameswaran and along with me, Irdina, Batrisyia and Vineshnaidu Suresh will help to present today's presentation. Hello everyone, I'm Thanussha Parameswaran and today I'm going to explain about the theory of the extended Debye-Huckle Law. The Debye-Huckle theory predicts that the activity coefficient gamma of an ion in solution decreases as the ionic strength of the solution increases. The activity coefficient is used to correct the behavior of ions in non-ideal solutions. The original Debye-Huckle equation works well for dilute solution with ionic strengths less than about 0.01 molarity. However, for more concentrated solutions, the interactions between ions become more complex and the simple relationship begins to fail. The extended Debye-Huckle theory modifies the original equation to account for more complex interactions that occur in moderately concentrated solutions up to 0.5 molarity ionic strength. The extended Debye-Huckle equation calculates the activity coefficient. An activity coefficient measures the behavior of ions in solution that do not behave ideally. In ideal solutions, it is assumed that the interaction between the particles are insignificant and do not contribute to the equilibrium. In non-ideal solutions, ionic atmosphere and ion size are taken into the consideration of an equilibrium.
So the formula of a standard Debye-Huckle law is obtained when the ionic strength of the solution is too high for the limiting law to be valid. So the activity coefficient may be estimated from the Debye-Huckle law. So here's the formula of the standard Debye-Huckle law, which is log gamma plus minus equals to minus A times the absolute value of Z plus Z minus times I with the power of half divided by 1 plus B times I with the power of half plus C times I. So I'll be explaining the symbols used in this formula, which is gamma plus minus, which stands for mean ionic activity coefficient. Z plus stands for cationic charge of electrolyte of gamma plus minus, while Z minus stands for an ionic charge of electrolyte of gamma plus minus, and I stands for ionic strength, while B stands for adjustable empirical parameter, and lastly, C stands for experimentally obtained value. So now we're going to move to the next example of calculation using the extended Debye-Huckle equation. So the question asks to calculate the mean ionic activity coefficient, which is gamma plus minus, for a 0.05 molar of natrium chloride solution using the extended Debye-Huckle equation at 25 degrees Celsius. So assume that the hydrated ionic radius of Na plus is equals to 0.3 nanometer and Cl minus is equals to 0.3 nanometer. So we need to know that the hydrated ionic radius stands for A of both ions. Okay, so now the given values here, we know that ionic strength, which is I, equals to 0.05 molar. The cation charge, which is Z plus, equals to plus 1. And the anion charge, which is Z minus, equals to negative 1. Okay, so A for both ions equals to 0.3 nanometer. So the constants here, we know that A equals to 0.509 mole with the power of negative 1 over 2, kg with the power of 1 over 2. And then B equals to 0.328 mole with the power of negative 1 over 2, kg with the power of 1 over 2, nanometer negative 1. So the value of C is equals to 0 since the values are not specified in the question. So it is considered negligible. So now we can insert the given values and also the constant values we knew into the equation of the extended Debye-Huckle law. Okay, so now log gamma plus minus is equals to negative 0.509 times the absolute value 1 times negative 1 times with 0.05 with the power of negative 1 with the power of 1 over 2 divided by 1 plus 0.328 times 0.3 times 0.05 with the power of half. Okay, so now we get log gamma plus minus equals to negative 0.1138 divided by 1.022. So now from here we calculate the estimated value is log gamma plus minus is equals to negative 0.1114. So from the value here, we can convert it into the gamma plus minus value, which stands for the mean activity coefficient, the ones that we are searching for. So gamma plus minus is equals to 10 power of negative 0.114, which is equals to 0.77 approximately. Therefore, the mean activity coefficient, which is gamma plus minus for natrium chloride in a 0.05 molar solution, is approximately 0.77.
Hi, so now I'm going to explain about the analogy of the Debye-Huckle Law. So first, the ionic atmosphere, a physical system involving a charged species, can be likened to a cloud of molecules surrounding a central ion, highlighting how their interaction with their environment around the ion, around the cloud of molecules, affects their concentration and activity. So the relationship between the concentration and activity in solutions is similar to colligative properties, where solutions behavior deviates from ideality due to solute interaction, similar how vapor pressure decreases with solute concentration. So the Debye-Huckle theories is very similar to the viral expansion in the gas theory, where in the gas theory the gas would expand in a very close manner. So it accounts for deviations in electrolytic solutions due to the electrostatic interactions among charged ions. So like how each charged ions will have their own electrostatic field. So when the charged ions come together, it will form an electrostatic interaction, similar to how the virial coefficients account for the intermolecular forces. See on the broader applications of the Debye-Huckle law. So the Debye-Huckle law, the Debye-Huckle equation is very crucial, very important in the electrochemistry field for calculating ion activity coefficients, aiding in understanding the reaction kinetics and the equilibria in batteries, fuel cell, and similar to it. So let's see. This law aids in predicting solubility and stability of ionic drugs in drug formation, guiding dosage form design under physiological conditions. So in plasma physics, plasma physics is a very fundamental theory that models interaction within the plasmas, focusing on the charged particles, which significantly or greatly influence the research in fusion energy and in the astrophysics field. The Debye-Huckle law also framework, the Debye-Huckle framework, the Debye-Huckle equation, the Debye-Huckle law aids in optimizing performance in material science by understanding ionic interactions for sensors on membranes which has ionic properties. So in environmental chemistry, the principles derived from the Debye-Huckle law are applied to predict the behavior of pollutants in the aqueous solutions. As we know, all in the aqueous solutions will have particles which have ions, will be freely moving ions. So this will impact. So when we use the Debye-Huckle law, it will impact the studies on water qualities or remediation strategies. So it will improve the water treatment strategies. So in biochemistry, in biological systems, this law helps explain the ionic interactions in cellular environments, influencing enzyme activity and biochemical reactions. The Debye-Huckle law also aids in modeling how ions affect protein folding and stability. So, the extended Debye-Huckle law graph effectively depicts how ionic activity coefficients change with the ionic strength, showing both initial rapid drops and subsequent leveling out as the concentration decreases. So, here is an example of a graph which shows the extended Debye-Huckle law. So, as we can see, the activity coefficient is given by the Davis equation, which is log f equals to negative 0.51 z square bracket square root I over 1 plus square root I minus zl. So based on that, the activity coefficient, which can be seen rapidly decreases and is slowly leveling out, which in the constant temperature, which is 25 degrees Celsius. So as it decreases, as the activity coefficient decreases and levels out, the ionic strength increases. So as we know this concept can only be applied in the extended law only, not in the limiting law. So like my friend said, already explained, the extended Debye-Huckle law is used to calculate the higher concentration of substance in an ionic solution. So this is one of the example of the extended Debye-Huckle law.
So that will be all from Group 19. Thank you very much.